Okay, so yesterday, what the hell were we talking about yesterday? Oh, we ended yesterday talking about amplifiers and special, versions of those amplifiers being frequency multipliers and mixers. So we're going to start today with chapter 4. And we're going to kind of bounce around chapter 4. Well, we're in chapter 4, but so we're still going to be in chapter 4. And we're going to go to page 4-18, 4-18. And we're going to talk about operational amplifiers, or just op-amps for short. And before we get headlong into all about op-amps, the operational amplifier is probably the, I guess you want to call it, the fundamental building block of analog electronics. And as a matter of fact, the earliest computers were analog computers. I'm talking electronic computers, not mechanical ones, were analog computers using operational amplifiers. Because operational amplifiers can add voltages or signals together. They can subtract signals from one another. They can multiply signals. They can do pretty complex math operations on signals, like integration and differentiation and all this kind of stuff. So they were used as analog computers in the early days. And you can actually still fiddle with all that if you want to. All it takes is a voltmeter. You don't need much. But an operational amplifier is basically, it's an integrated circuit. It's a blob. It can have anywhere from about 4 to 2,000 transistors in it. Doesn't necessarily have to be transistors. It may be FETs, MOSFETs and stuff. But the devices inside that chip, we kind of ignore them. We don't really care what they are or how they're fixed up. We're just going to treat it like a block in a block diagram. And so like any amplifier, it's got an input and an output. An operational amplifier is a little bit different in the fact that it actually has 2 inputs. And I'll just jump up on the board here and draw it very quickly. I'm not going to spend too much time on the board with this, I hope. So an operational amplifier is just typically drawn as a big arrowhead kind of thing. This is the output. And it has 2 inputs. And the inputs are marked plus and minus. And if you're not familiar with them, that can be very misleading. It doesn't need positive and negative, the plus and minus. Okay? And when we talk about an amplifier, what we're talking about with the plus and minus is if we insert a signal into that input, it's going to come out the same direction. In other words, it's not going to be inverted. If we put a signal into the minus, it's going to come out upside down. Okay, so that's all it is. It's called a non-inverting and an inverting input. Okay, so that's what the op-amps are, and this representation of them. Say inside this triangle, there could be a couple of hundred FETs and transistors and resistors and diodes and all kinds of stuff. We don't particularly care. We're going to treat it kind of as a block and stuff like that. But yeah, this is kind of the universal representation of just this arrowhead kind of triangle thing with a plus and a minus. And keep in mind that that plus and minus is not talking about positive and negative anymore. It's talking about, is the signal going to be inverted or flipped upside down when it gets amplified, or is it going to be left alone? So that's inverting and non-inverting inputs is what the plus and minus says.
Is that explicitly explained in the book somewhere?
Yeah, somewhere. The operational amplifier, this box, the perfect amplifier in the world that you would want to use for almost any purpose, whether it's amplifying audio or amplifying radio frequencies and stuff, a perfect amplifier would have an extremely high input impedance, infinite, that would be perfect. It would have an extremely low output impedance, like 0 ohms, that would be perfect. And it would have a very, very high forward gain, preferably infinite. That's the perfect amplifier, okay? So an operational amplifier tries to get close to that perfection. So an operational amplifier has a very, very high input impedance, which means you can drive it with very, very small signals in the order of microvolts, and it'll work quite well. They do have a very low output impedance in the order of 1 ohm, something like that, very low. Gains, a poor operational amplifier would have a forward gain of 100,000. That's a crappy one. If you want to spend more than 10 cents and you go spend $1.75 and buy an instrumentation grade operational amplifier, it would have a forward gain of 25 million. Not bad, you know. Put 1 microvolt in and get 25 volts out. Now that's gain. Okay, so these things are they're just an integrated circuit, you know, a blob with some wires hooked to them. They perform very well. They're not the perfect amplifier, but they're darn close. You know, for most applications, they work really well. And so on, one of the things is just the definition of what is an op amp. This is one of the questions on the exam. And on page 4-18, it's 1, 2, 3, 4, 5. The 6th paragraph down, where the paragraph starts with, an op amp is a high gain, direct coupled differential amplifier. Functional characteristics are determined by external components, have high input impedance, extremely low output impedance, extremely high gain, flat frequency response. The ideal op amp would have an infinitely high input impedance and a 0 output impedance. You can highlight that whole paragraph with your highlighters. Everybody got that one? So, once again, we talked about the ideal op amp specs are infinite input impedance, 0 output impedance, infinite gain, and infinite frequency response. That would be perfect. In real world, that doesn't happen, but you can buy op amps that go up to 77, 78 gigahertz. That's pretty good bandwidth. And I'm talking DC to like 80 gigahertz. And it will amplify all that. You know, so, and that op amp might cost you $5. You know, these things are so mass produced because they're used everywhere that the price on these things is extremely reasonable and cheap. So they do have ones, by the way, since we're talking radio, because this is what we're all here for, is radio. There are op amps that are designed specifically for RF frequencies, and they actually don't work that good at low frequencies like that on audio and stuff like that. So, and there's tons and tons and tons. There's hundreds of thousands of varieties of them out there. So, what else am I supposed to say about op amp? If we have this amplifier that's got a gain of 500,000, that's a little bit ridiculous because there's very few circumstances where you want that much gain. So we need some way of controlling the gain of the device. And the gain of the device is controlled by something called feedback. And what the heck is feedback, you ask? If we have our amplifier, we'll just stick with this diagram I have here, it's fine. If we put a signal into, let's say, the inverting input, and this thing has a gain of 500,000, which is not unusual for an op amp, that signal is going to come out 500,000 times larger, and that's an awful lot of gain. One thing we didn't draw here is power supplies. Okay, op amps run on what we call a split rail power supply, so they have a positive power supply and a negative power supply, and ground is in between. So obviously this output voltage can't go any higher than our power supply. So if our power supply is, say, plus minus 12 volts, and we go to amplify a 1 volt signal and we amplify it 500,000 times, you're not going to get 500,000 volts out. You're going to get the power supplies, or what we call the rails. The signal's going to hit the rail and stop. Okay, so we need some way to tone this thing down. And the way to tone this thing down is we take and we connect the output and we come through a resistor network back to the input, and another resistor here to ground. Okay, so what we're doing is we're taking some of the output of this amplifier and feeding it back into the input. That makes sense? So if we put a AC signal in like this.
Can I steal your yellow highlighter? Mine died.
Yeah, go ahead.
I thought I was being smart and being good with it.
Never fails. So if we put that sine wave signal into the input, on the output we're going to get a much taller, but it's going to be inverted, right? Because we're going into the inverting input. So anything into this minus sign comes flipped 180 degrees. So this is going to come back in, and since we have an inverted signal, it's going to add to our non-inverted signal, and the two are going to basically effectively cancel each other out. As a matter of fact, if we had no resistor in here, if we tied just a straight wire between there and there, we would have a gain of 0. In other words, voltage in equals voltage out. Okay? But by changing the value of these resistors, we'll just call this one R1 and R2, by changing the ratio of these resistors, we can control how much of this output signal we feed back into the input, and therefore we can adjust the overall gain of this just by the ratio of these resistors. Okay, if this resistor is 100 times bigger than that resistor, our gain happens to be 100. So it's just a simple matter of picking the value of two external components to adjust the gain of this. So if we want to design an amplifier with a gain of 100, if we're going from a small signal and we want something 100 times bigger, we just simply choose these two resistors. So the ratio of these two resistors is 100 to 1. In other words, this one's, let's say, 100,000 ohms, and this is 1,000 ohms. Done. We have 100 gain on our amplifier. It's just a very, very easy way by choosing really cheap and expensive parts. And of course, resistors can be made variable. So if we want a variable gain amplifier, well, you can just simply say that one's variable, and now you have a knob on the front where you can vary the gain of your amplifier. Call it a volume control if you're talking an audio amplifier. Call it an RF gain control if you're talking an RF amplifier. But simple as that. So, what else am I supposed to say here? Okay. Back in the book there, at the bottom of page 4-18, there's a little schematic diagram, and you can see how they drew the amplifier there with just kind of that arrowhead with the inverting and the non-inverting inputs, the plus and the minuses there. They did include power supplies. In their case, they're using plus and minus 10 volt power supplies in the output, and you can see that they're using feedback through R2, and you can calculate the feedback networks and all that kind of stuff. Isn't that just the most fun? Problem with op amps is, like anything, they're actually not that perfect. So in theory, a theoretical op amp, it doesn't matter if you put a signal into the inverting or the non-inverting or the plus and minus inputs, it's going to come out identical. Well, the fact of the matter is, in real life, that's virtually impossible to do that. So there's always a slight difference between the inverting and the non-inverting. Okay. And the reason is that there's all kinds of transistors and diodes and stuff inside this block that we don't really care about, and it's impossible to match these things perfectly. Really, what happens is the inverting input goes into a transistor and the non-inverting input goes into another transistor, and they get mixed together later. And those two transistors, unless they're absolutely perfectly matched, which you can't do, you can get damn close, but you cannot do it perfectly, there happens to be an imbalance between the two. And that actually shows up as a voltage. You can actually take a voltmeter, you can tie one of those inputs directly to ground so its voltage is at 0, And if you measure the voltage on the other pin, if it's a perfect op amp, it would be 0 too, because it'd be identical, but in fact it's not. So there's something called an offset voltage. Okay. It's a bit of a pain in the arse, offset voltages, because it's an actual DC voltage. Usually it's not too desirable. These amplifiers will amplify DC, by the way. Put in a 1 volt DC, and if it's got a gain of 10, you'll get 10 volts DC out. That's why they were used for analog computers. Basically, it was just DC voltages they used. So to multiply and add and stuff like that. So, like I say, things aren't perfect. There is slight differences between them, and input offset voltage is, in the early days of op amps, it was a big problem getting rid of these offset voltages because manufacturers couldn't match the transistors that well, or FETs if it happened to be FETs in the front. And there was all kinds of designs and circuitry, and engineers spent days and hours and weeks and weeks and weeks coming up with circuits to compensate for input offset voltages. Nowadays, even the 6.5 cent op amps that you can buy, if you buy them by a quantity of 100, they're about 6.5 cents. Their input offset voltages are thousandths of a volt. I mean, it's still there, but it's incredibly small. And once again, if you go out and you spend, say, $100 on an instrumentation grade op amp, the input voltages you can't even measure. They're like 10 to the minus 12 of a volt or something. They're still there, but the manufacturers have taken it upon themselves to design these things better, build in all this composition into the chip so you don't have to worry about it anymore. So, isn't that just the most fun? We talked about, yesterday we talked about filters. Remember when we used coils and capacitors in various combinations to build a bandpass filter, a band notch filter, a band stop filter, and a low pass filter, and a high pass filter and stuff? Well, the problem with all those filters is there's loss through them. The output signal is always going to be smaller than the input signal. But if we have an amplifier that can amplify everything from DC to gigahertz, why not just throw that amplifier in there, put our capacitors and coils around it, and use its amplification to make up for that loss that's in the circuit? And so that basically comes up to what we call an active filter. Active because it has an amplifying component in it. So the filter is no different than what we had drawn out yesterday, where it's, a coil, a capacitor, or a series of coil and capacitors and whatnot, giving you a high pass or a low pass or a band pass or a notch or a band stop filter and stuff. But all we do is we throw an amplifier into that mix to make up for the losses in all those components, and we end up with an active filter. And there are 2,500 page textbooks on active filter design. It's a huge topic. You can do active filters to do all kinds of stuff. We're just going to touch on them very, very lightly. So, as a matter of fact, active filters you can actually use, because these amplifiers have so much gain, you can actually have a filter that amplifies too. It doesn't necessarily have to be unity gain. Unity gain meaning the input and the output are identical. You can actually amplify if you want to. The last thing before we move on from operational amplifiers is we talked about this blob or this block with these two inputs, this inverting and non-inverting input. Okay? So the question is, what happens if you take a signal and you apply it to both inputs? Right? This is where it gets interesting. Okay? So if you take a signal and you apply the signal to both inputs, all things being equal, you should get 0 out. Because the inverting is exactly going to cancel the non-inverting. Okay? That makes sense? Okay? So anything that is common to those two inputs, in other words, any voltages or any signal that is common to them, in other words, identical on both, is going to get canceled away. Anything that's different between those two is going to get amplified. Okay, so an op-amp is technically what we call a differential amplifier. You're amplifying the differences between those two inputs. Is what you're really doing in the end. Okay, so it's a differential amplifier. And once again, early computers, you wanted to subtract. So these things can add voltages, these things can subtract voltages, these things can do all kinds of neat stuff. So you may hear the term differential amplifier thrown around, and every op-amp out there is a differential amplifier. Differential meaning you're amplifying the difference between those two inputs. Okay? So I'll just throw that one at you. And you're wondering, why would you ever want to do that?
Find something hidden in there?
Cancel noise.
Cancel noise.
Cancel noise is a really good answer, yes.
That's what these noise canceling headsets are. You're actually feeding it through a differential op-amp to get the noise cancelled.
Vanity and servos too.
Yep, lots of things. Anybody drive a vehicle that's newer than about 1996? I know there's at least one mechanic in the room, and the mechanic can tell you that there's multiple computers inside modern vehicles. There's a computer for your engine, there's a computer for your transmission, there's a computer for your power door locks, there's a computer for your dashboard instruments. All these computers talk to each other in real, you don't even know. When you turn the key on, they power up and they start talking to each other. And your vehicle is actually a fairly complex data network. Well, all that data networking is done on differential pairs. In other words, there's actually two wires connecting all these computers together, and they're all interlinked all over your car or truck or whatever kind of vehicle you're driving. And the reason they use differential pairs is an automobile is a noisy source. I'm talking electrically noisy. You have things switching on and off. You got guys using their two-way radios. You've got, pull up beside other noisy vehicles or other RF sources and stuff. And so if you take these tiny little digital signals that these computers are pumping all around your car, and you put them on a differential pair, and first thing it does is go into a differential amplifier, anything that is common to both of those wires gets thrown away. And common noise is just that. If there's an outside interference coming in and slicing through that wire, we talked that whenever an electromagnetic field slices through a wire, it produces a voltage. Well, that voltage can very easily look like garbage data to a computer, and the computer could just hang up. But the thing is, an outside interfering is going to slice through both of those wires, and it's going to induce the same voltage or the same noise on both of those wires. So when it gets to its destination and hits that amplifier, anything that is identical on those two wires is gone, and you're only amplifying the difference. Okay? So, and that, by the way, is called the CAN bus. The CAN bus is what most vehicles use nowadays. Yeah, and well, CAN is actually, it's a standards organization of some kind. You can ask the mechanic at the table, he'll tell you.
Circuit 800.
Yep. And stuff like that. But there's a primary example of where what we call balanced two-wire technology is used in communications. So, and there's lots of others.
Well, using some of these things in such a way now that even the wire length comes into time for the time constant. There's some of that I know.
Yeah, in professional audio, for example, microphone cables and all that kind of stuff are all balanced.
Even on some of the big trucks, you got to watch your harnesses. They're specific because it's all common paths.
Yeah. So okay, so we're going to leave. What's the advantage of using an op-amp in a audio frequency LC circuit? In other words, an active filter. What's the advantage of using op amp in the LC or in an audio frequency LC circuit is you make up losses in the components. You could actually have gain if you want to, but it basically it makes up for the losses. It's an active filter. So the other thing is, since it's a differential amplifier and it's in this circuit, if there happens to be stray magnetic fields, somebody transmitting on their radio nearby, this common mode rejection, that's what they call it by the way, is CMRR, common mode rejection ratio, will reject all that. So it has the added advantage that it helps to reduce hum and noise too by having it in your active filter. So fun, isn't it though? Okay. We're gonna jump ahead a little bit to page 4-23. So that's it for op amps. Op amps are really cool, by the way. They're cheap. The only problem is they want 2 power supplies, a plus and a minus. And engineers and designers and hobbyists have complained for years, I love op amps, but I hate the fact that you have to have 2 power supplies. And so manufacturers now have complete lines, very broad lines of single power supply op amps. So you don't really need the 2 anymore. You can buy single, what they call single rail op amps that only need just 1 voltage power supply, and they work just fine. Like I say, once again, the manufacturers answer the call. If there's a demand, somebody will meet it, right? So, you know, for example, if we go back to automotive, so all the op amps used in automotives are all single rail because you got plus 12 volts. Well, technically you got plus 13.8. Everybody knows that a 12 volt battery is actually 13.2, right? Well, 13.2 static, 13.8 after a full charge, and it could actually be like 14 plus fresh off the alternator, but yeah, and all that stuff, so.
14.4.
Yeah. The nominal voltage for a lead acid cell is 2.2 volts. So 2.2 times 6 is what?
13.20.
Yeah. 13.2. Yeah. Yeah. So when we say 12 volt power supplies, all of our ham radio stuff, if you hook a meter to it, it's not 12 volts, it's going to be 13.2, 13.8. That's what an automobile puts out. So, grounded grid amplifier. Yesterday, remember, we very briefly talked about vacuum tubes, and actually on the page before that, on 4-22, they show anode and the grid and the cathode and filaments and all that stuff. Once again, that is not necessary for the exam to know the actual components. However, on page 4-23, where they're talking about the grounded grid amplifier, there are questions on that. And I'm not going to bother rewriting the schematic on the board. They have a nice schematic in the book here. And I'm going to just point out some stuff for you to highlight on that page. So we have a lovely looking schematic of a grounded grid amplifier. Let's just quickly go over it. On the far left, you can see a round looking circle there that says input. That input goes through a C1 and an L1 and a C2 and a C3, and it goes right into the cathode of the tube. And notice the cathode of the tube, the little filament, the little heater, the arrow pointing thing is down there, and you can see that it has actually a separate transformer, and it's fed by AC to heat up that heater. And remember, the only function of the heater is to heat up that cathode to make it hot so the electrons will boil off and stuff. But you can see that the filament down there is tied in, and they've got, what is it, C8 and C9 tied across the filament and all kinds of stuff like that. So that part down there is just simply to light up the tube. That's the thing that gives it its lovely glow, its warm appeal.
It's warm.
Yeah, the grid of the tube, which is kind of that screen thing in between the 2 plates, is grounded because this is a grounded grid amplifier. Surprise, surprise. And then the anode, or the plate, which is the top portion of the tube, if we just go straight up from there, you'll see we go through a couple of RF chokes and one C4, and we go to the supply positive voltage is too high. You know, it should be a positive high voltage supply. The name for that is the B+. That's the high voltage supply. Also tapped off the plate going to the right, we go through C5, and then we go through a couple of variable capacitors and a couple of 3 coils, and then we finally get to the output. So input is, remember this is an RF amplifier, so it's RF at some point, more than likely HF. And it comes in, gets amplified by the tube, we're using the amplification factor of the tube, and gets pooped out the back. Okay. So we're going to go through some of the components on here and figure out what some of these things do. And why don't we start at the input? And so right on the input, the first thing we see is C1 going to ground, L1 in series, and then C2 going to ground. So that C1, C2, and L1, okay, that is, what does it do?
Filter.
It is, what kind of filter? High pass, low pass, band pass, notch? Well, ignore everything to the right of it. Okay, just go back and think, okay, if it's a really low frequency like DC, is it going to go through? Yeah. If it's a really high frequency like gigahertz, is it going to go through? No. The capacitors are going to sewer it right to ground and the coil is going to say no. So it is a low pass filter. So if this is an HF power amplifier, right there you want to be filtering off everything above roughly 30 megahertz. Yeah. So the first thing we do is go into a low pass filter. So we're already cleaning up whatever signal's coming in. We're good engineers, we're designing a good clean amplifier, so we want to keep things nice and clean. So the first thing it hits is this low pass filter. Then we go into C3. What is that C3 doing there?
We start with the DC.
Okay. It will stop any DC that might be coming in from that circuit previous to us, because remember that coil, that L1, it's a piece of wire to DC. So if there happens to be any DC from the circuit previous, we don't know. I mean, we were told to build an amplifier. We don't know what you're hooking to the amplifier. There might be some DC that you're hooking up there. So just make absolutely sure we're not going to disturb the operation of our amplifier. We want to block any DC, but we want to let the RF through. So that C3 is a blocking capacitor. Okay, so it just simply blocks any DC, but lets the desired RF signal through onto the cathode of our tube. Okay. Also on the cathode of our tube, on that other side of C3 where the tube is, you notice there's a little connection going up through RFC1, and it says to high voltage negative supply, which is your B minus, by the way, if you want to use the proper term for it. Okay. What is RFC1 doing there? What's its function?
Should block any RF going back to the power supply.
Precisely, yep. Just remember that a power supply is as good as a ground to RF. Power supplies, remember, have big capacitors in them, and real good bypass. RF will just squirt through a capacitor, through a power supply to ground, just as if it's a ground connection. So once again, we don't want any of RF to go back to the power supply. We want to keep all the RF in the tube to do its work. So that RFC1 just is a blocker, lets the DC voltage come down onto the cathode of the tube, but doesn't let the RF go out. We want the RF to go into the tube and do all the work for us. Okay. Now, looking on the plate or the anode of the tube and going straight up to the B plus supply, once again you see there's RFC2, RFC3, and C4. And those again are RF blockers. We need high voltage on that plate, and this could be in the order of hundreds or even thousands of volts on that plate, but we don't want the RF to go back and disappear into our power supply. We want RF to go to the output. So that RFC2, RFC3, and C4 are stopping any RF from getting back into the power supply. That makes sense? So the only place the RF has left to go is to the right through C5. And what's the function of C5?
Just stop any of the DC coming.
Yeah, once again, the B plus up there, that B plus could be 3,000 volts. Could be even higher than 3,000 volts. If C5 was not there, that DC voltage would be right on the output. So unless you want to reach out and touch the center pin of the coax on your tube amplifier, I would strongly advise you make sure you put a capacitor like C5 in there. And if you go to a flea market and you buy an old tube amplifier, before you even plug it in and turn it on, you take it apart and you make damn sure that that blocking capacitor, that's a DC blocking capacitor, stops that high voltage but lets the RF go through. You make damn sure it's there, because those power supplies are high voltage and high current. They are lethal. Okay, so it's a safety thing. If that blocking capacitor is shorted out or has been removed or whatever, because you bought this at a flea market, you don't know the history of it, you don't even turn it on. You open the cover and you start checking and looking at things like this. So C5 is a blocking capacitor. So it lets the RF through but blocks any of the DC coming from the B plus. Okay, then we've got, oh, what is it there? C6, C7, L2. What the heck is that? This one here is something we really haven't talked much about, but
Filters,
well, it's kind of a filter, yeah. But it's got variable capacitors. Notice that what is it? C8 and C7 there? Is it C6 and C7 are variable capacitors? So these would actually be knobs that you can tune on the front of this power amplifier. And yes, the early ones had tuning knobs, and one would be called plate and one would usually be called load. The C6 would usually be labeled plate and C7 would usually be labeled load. Okay, now we haven't really started talking about antennas and transmission lines and all this, but almost all of our ham radio antennas are 50 ohm antennas. Okay. The output of this tube is in the order of a couple of 100,000 ohms. Okay. RF, if we want maximum power transfer, we want to transfer to the same impedance. So if we've got a 50 ohm antenna, we want our transmitter to be 50 ohms, and therefore the maximum amount of power transfer between it. So that network, it is, by the way, a low pass filter. That's one advantage. But its real purpose in life is to match the high output impedance of the tube down to the reasonably low impedance of our antenna. It's an antenna matcher. It does function as a low pass filter though too. So it's kind of a 2-for-1. And depending on what kind of antenna load you put out there, you may just throw up a random wire in the yard, or you may have a commercial Yagi or a commercial vertical or something like that. Every frequency you're going to go on, the impedance of the antenna is going to be slightly different. So these tuning controls give you the opportunity to match this up so you get maximum power transfer out to your antenna. It's basically an antenna matching network.
So that would eliminate a separate tuner.
Yes. Yep.
I have a question about, let's say RFC3 or RFC2. It's in the schematic. It's drawn as a coil.
Yep.
But it's called a C. Why is that?
Choke.
Oh, is that for choke?
Yeah. Yeah. The name choke and the name coil are choke basically is used when the coil is blocking something or choking something. Okay.
Okay.
So RFC is radio frequency choke. So
So
yep.
it's-
No, good question. Yeah.
So is it a coil?
Yes, it's a coil.
It's only coil.
It's just a coil. Yep.
Okay.
Okay. So like I say, that little network of the two variable capacitors and L2 is a low pass filter. It's basically matching the high impedance of the plate on the tube to a reasonably low impedance of our antenna system. And yes, if you have wide enough variation on those capacitors, it effectively is your antenna tuner. Okay. Okay. We kind of ignored the filament down in the bottom there. And most of the times when we talk about tubes, we do ignore the filament. The filament is provided with a voltage, AC or DC, it doesn't matter, and it just lights up and heats up the tube. Okay, but there's a little more to the filament than just being a dumbass heater. Okay, and the problem is that this is an amplifier, and this amplifier is relying on those free electrons being available. So the heater comes on and heats up this plate red hot. This plate is boiling these electrons off. Sounds all fine and dandy. But what happens if the heater is not constant? Okay? So the supply of electrons is not constant. It may vary. And if the heater happens to get a little bit of our transmitted RF into it, and the heater actually starts varying with our signal, some really odd things can happen. I can see everybody's eyes going, yeah, this is interesting. So to do this, we, especially in an RF amplifier, not so much in audio where frequencies are much lower, but in RF amplifiers, we actually need to pay attention to the filaments or to the heaters. And we have to make sure that the heaters don't get any stray signals induced into them. We want them to just be a continuous heat source, and that's it. And so the first thing that we do in this case is we actually have a separate power transformer that feeds that filament. And why would we do that? Why not just take a DC voltage from somewhere else and do it? And the answer is, well, anybody know what the answer is?
Used to be cost.
So, if some RF is picked up across the heater, okay, theoretically the RF is going to slice into both sides of those heater wires that's the same, right? And once again, this comes back to common mode rejection. We talked about common mode rejection with our op amps. Well, this is a transformer. Believe it or not, transformers have really good common mode rejection. Any signals that are induced on those two wires that are in phase with each other are going to simply cancel out in the wire. Okay, so remember, this thing is sitting in a cabinet and there's lots of RF. There's probably 50 or 100 watts of RF coming in from the transmitter that's driving this thing, and there's going to be 1,000 watts plus going out. There's lots of RF here. There's RF going to be floating everywhere, and no matter how well you shield this thing and build cabinets around it and stuff, there's going to be stray RF. You really can't get away from it. So any RF that is floating around in this cabinet is going to go through every little piece of wire. And every little piece of wire you can now think of is a little tiny antenna. Normally we wouldn't even think of it, but remember, we're talking some power here. We're putting up some pretty good levels of RF. So even those little filament leads that are, a couple of centimeters long are in fact a little tiny antenna. And the RF can slice into those, and once the RF slices into, now we've put an extra signal on our heater, and our heater, instead of being this nice continuous source of heat and electrons, starts dancing up and down as you're speaking to your microphone. Not a good thing, believe me. So simply by using a transformer, just like they show in the picture here, any RF induced on one of those leads is going to be pretty much induced on the second lead, and they're just simply going to cancel each other out. So it's common mode cancellation is one reason for it. And then the other thing they do to make sure RF is drained completely off that is they hook those two capacitors, what is it, C8 and C9 across them, Those are RF bypass capacitors. Any RF that may be remaining on that filament, we want to get rid of it off the ground. We want the filament to just give us a nice constant glow, and that's it. So just a little bit of stuff to think about here. Got to remember that we're working in an area where we have very strong RF signals, and even a short little piece of wire will pick up stuff. So it's not like DC or even audio electronics where that much wire you don't even think about, right? Well, now we have to think about it, so. What else am I supposed to say here? Because, once again, because every piece of wire in this circuit is now acting as a miniature antenna, an amplifier can turn into an oscillator in a really quick time. And what is an oscillator? An oscillator is an amplifier with positive feedback. We looked at negative feedback up there. Well, what happens if we feed back into the non-inverting input of the amplifier? The thing goes crazy. It starts oscillating. Amplifiers turn into oscillators really quick when the feedback accidentally becomes positive instead of negative. Now, in the RF world, we use positive feedback and oscillators to our advantage because we want to create frequencies, okay? But in amplifiers are supposed to amplify, they're not supposed to oscillate. And once again, we're in a situation here where a length of wire that long can actually pick up some of our signal and feed it back into the circuit. So we can have completely unintended, stray feedback paths that we never thought of. And oops, my amplifier, my 1,000-watt amplifier, oh yeah, it's putting out 1,000 watts at 55 megahertz or some frequency way outside the band. And you're looking at it, oh, look at all this power output, but hang on, I'm not putting any power into it. What's happening? Okay, what's happening is we've achieved a positive feedback path somewhere in there. And so what happens is you have to go through the amplifier and you have to add RF bypass capacitors to ground and series chokes to stop RF from getting into various places. And that whole process of going back and, shall we say, tweaking your design is called neutralization. We need to neutralize the amplifier so any of that positive feedback is gone. In a well-designed, well-bent amplifier, a lot of times you get lucky and you don't have to do it. But you will see, even in commercial, amplifiers that you buy, grounded grade amps or other large solid-state power amps now, they will build the thing on the assembly line, put it all together, and when they go to test it, the guy will sit there with a soldering iron and capacitors and solder them in by hand to fix all the neutralization problems. Because there's just such slight differences in components and lead length and everything else that no two are the same. So you can't just cookie cutter out an amplifier, and that's one reason that these high power RF amplifiers are expensive. It's nothing that you can just mass produce and ship out the door. You produce one, you have to have someone sit down, put it on a test bench, put spectrum analyzers on it, and sit there with capacitors soldering in by hand until it's neutralized. Then they can pack it up and ship it out. And that's an expensive process. And I don't know if you've been shopping around for HF power amplifiers, you can't touch these things for under a couple of grand a piece. And that's one of the reasons why. It's a very difficult thing to build in a mass production cookie cutter thing. As a matter of fact, it's impossible. So there's a lot of extra labor that goes into these things. And chances are you may buy one of these at a flea market for a couple of $100 and get it home. So it's nice to be aware that when you open this thing up, you're going to have a schematic like we have here in the book. But when you look at it, you're going to say, well, hang on, there's an extra capacitor here and an extra coil there and this kind of stuff that doesn't show up on these pictures. And what that was the manufacturer going back to neutralize, get rid of all those positive feedback, all those oscillations to make the thing work. Okay? So, like I say, just beware of it. It's lots of fun. So the output tuning controls on the transmitter power amplifier allow efficient power transfer to the antenna. I think we kind of said that, right? The filament transformer secondary is usually connected directly to the vacuum tube. It doesn't go anywhere else, just like they show in the schematic there. Okay, so that AC filament source is strictly for filament and nothing else, and the reason is that common mode rejection to get any induced RF off of it. Some filament transformers will have a center tap, and the center tap will be tied to ground. And once again, that's just another way to give a path for the RF to get to ground. We don't want the RF going into the filament. Okay. The filament legs have a capacitor tied to ground for what purpose? This is a question on the exam. To RF bypass, yeah. In a grounded grid amplifier, the input signal connects to the cathode. That's a question on the exam. In a grounded grid amplifier, the plate connects to a pi network through a blocking capacitor. So in other words, just get familiar with this little schematic. In a grounded grid amplifier, the plate choke connects to B plus.
That's positive.
Yeah, positive supply, or the B plus, yeah. And the answer on the exam, by the way, is B plus. They don't say positive supply, they say B plus. So take your pen or pencil and write B plus up there. Okay. The grounded grid cathode choke connects to B minus, or bias is another word for that, by the way. But the exam, the answer is B minus. So the Industry Canada guys, or ISED, whatever they call themselves, use B plus and B minus for those terms, which are the old, the guys who worked on tube equipment, they know all about B pluses and B minuses and all that kind of stuff. So, what does neutralization in a grounded grid amplifier circuit do? Cancels the effect of positive feedback to eliminate oscillations. And by the way, these oscillations can be at almost any frequency. They may not even be in the HF band. They can be totally random. Okay. Neutralization in vacuum tube amps cancels oscillation caused by inter-electrode capacitance. There's a word for you. But that's one of the questions on the exam. They're talking about neutralization. Intra-electrode capacitance. In other words, two pieces of wire running in the chassis. Well, once again, two conductors separated by a dielectric makes a capacitor, and at certain frequencies, well, the RF will go right through there. Parasitic oscillations are caused by a lack of neutralization. In other words, if you have an amplifier that's giving you an oscillation at a weird frequency, you have to add some neutralization to it. There, I think we've talked the grounded grid amplifier to death. I think that's about it. See, I have stuff highlighted on my page. See? Yeah, see?
Oh, yeah.
Really good. Yep. Basically, that schematic is kind of the key to it. Just as long as you realize the B plus and the B minus, label those, and they're pretty good to go. And they do have a good discussion on this page, talking about every component in there and its function and whatnot. So it's still a good thing to know, because especially at flea markets and stuff, you can still buy HF call them boot amplifiers, power amplifiers for reasonable prices, and almost all of them have tube, final, grounded grid configuration. It's a real classic configuration, so it is a handy thing to know about. And like I say, they ask questions about the grounded grid amp on the exam, but they don't really ask any other questions about vacuum tubes at all. So, yeah, what do you do? What we're going to do is we're going to take a 10-minute break, and we're going to come back at 10:10.